Hello and welcome back for another presentation, this one on your introduction to minerals. So this is going to be a presentation system that's going to build off of each other, be broken into two parts. First part minerals, and then we'll move forward after that into introduction to rocks. But before we can get to rocks, we have to understand the foundation and building blocks of minerals. So let's get going. So again, we're going to be starting off with an introduction to minerals. So what is a mineral? Well, there's a couple attributes to the definition of what a mineral is. So we're going to work through that, and then we'll learn how to identify things that are or may not be actual minerals. So the first part is minerals are made up of at least one or more element. So take yourself back to when you took a chemistry class or you took some science course and they had the periodic table of elements. Well, those are really the building blocks of minerals. So minerals are made out of one or more element that can create a compound. The next part of that definition is minerals are defined as being naturally occurring, which means they must come from nature. They're not human made. The second part is they must be inorganic, meaning it could not have grown from a plant. The next part of that is that they must be well defined with their chemical composition and an ordered atomic arrangement, meaning a crystalline. So what does that mean? Well, that last part in specific means that minerals have a very distinct recipe that make it what it is. So that being said, as an example, quartz. Quartz is a very common mineral, but there's different variations. There's yellow quartz, there's white quartz, there's gray quartz, there's a pink and a purple. So all of those have very distinct recipes. Okay, so just think about it. It's like we have a cake, but we have different variations of that cake, but we know specifically what part of that recipe needs to change in order to make it a little bit different. Another thing, since I've mentioned it, inorganic means that it cannot come from plants. So perhaps you've been to places where they sell rock candy or they sell the crystal sugar cubes on a stick and they say that this is a mineral. It's not a mineral, right? Because we know that sugar is glucose, which comes from plants. So when you're buying a lot of your drinks, your fancy drinks and stuff like that, your energy stuff, and it says that it's full of minerals, it's probably meaning that it's got potassium and salt, which are both genuine minerals, but everything else is chemically made. It's made by humans or it's made by a plant, so it doesn't really count as having a mineral in it. So moving forward, minerals also have physical properties such as color, luster, hardness, streak, and cleavage or fracture. We will be spending some time going through each one of those, but those are really just observational features. So what is the actual color of that specimen? Luster is really how does it reflect light? So is it dull or is it metallic-y or is it glassy? We can look at the hardness, physically how hard is that specimen. Streak is the color left behind when you scratch it on a tile. And then how does it break? Does it break into a pattern or does it just shatter like glass? That'll be cleavage versus fracture. That being said, the International Mineralogical Association has recognized nearly 5,500 different minerals. Again, many of these are variations of the same. Again, like I use that that analogy with a cake. We have cake, but is it strawberry, vanilla, cherry, raspberry, boysenberry? What is the variation of that? So they're all individually different, but yet it's part of that same grouping. So I hope that helps. Moving forward, we'll move into the story of a mineral. So where does it begin? Well, it begins with the story of atoms and elements. And then they are able to come together into a proper proportion, meaning a recipe. So often in geology courses, you'll learn, you're looking at the chemical bonds, and it's like those, you probably have seen them. They're little wooden balls that have metal brackets between them and to show the chemical composition, the compound of that foundation. And that's where this begins. Things that take into consideration time, temperature, and space. You need to have an actual time allotment for these, at usually at one point, molten materials to then come together. And then you need that time for it to cool down to crystallize. You also need the time for the temperature, and you also need the actual physical space. We find that many crystalline structures can be constricted based on the space, whether it be small or large. An example of that would be like looking at a geode. A geode are those rocks that you cut in half and inside have a mineral crystalline structure. Sometimes if it has too much time and not enough space, that geode will just fill completely with crystals where there's really no nice design. It's called a thunder egg because it's solid. Or maybe you have very small crystals because it cooled very quickly and it had lots of space. You've got lots of little crystals inside. That being said, the last part here is as atoms keep being added in this array or style, repeating that basic arrangement, the creation of crystals becomes bigger and the development becomes more clear. So versus having a very small crystal versus seeing very large ones, how much time was allotted for that to occur? We find that, especially in the development and crystallization of minerals, that the longer you have in time, the larger the crystals will be present or observed. All right, so moving forward, let's start talking about some of these physical properties. So I brought forth these in 2 slides ago: color, luster, hardness, streak, cleavage, or fracture. So we'll talk about these here, and then I actually have a slide for each one that we'll be able to look a little bit more in depth to. So the first thing is color. Color is the most obvious, but it's actually probably the least helpful out of all physical properties. I often I compare the color of minerals to the color of people. It's the most obvious thing that you see when you look at someone. It's the first thing you pick out: the color of their hair, the color of their eyebrows, the color of their skin, their teeth, their eyes. But does that color that you're observing allow you to make some form of association or some form of conclusion? Well, oh, because their hair is this color, that means they must be like this type of person. That doesn't mean anything. It's an obvious trait, but it's really probably the least helpful. So when we learn to identify minerals, that's, even though it's the first thing you see, we try to keep it to be the last thing that we use. Why? Well, because like I said earlier, we can find that many minerals have, it may be one type of mineral, but different variations. So as an example, we'll talk about, this is a quartz crystal. This is a double terminal quartz crystal, has not been cut. This is the way it was collected. But this one in particular is considered lemon quartz because it has a very, very light, yellow shade to it that's within it. Well, that being said, there's yellow quartz, there's smoky quartz, there's going to be rose quartz, which is more pink. There's purple quartz, which is amethyst. So again, just because it's yellow doesn't mean it's quartz. If it's yellow, it can be quartz. It could be apatite. It could be a different variation of fluorite. I mean, it doesn't really narrow it down too much. So although it is the first property we see, it's probably the least helpful. Moving forward, the next one we have here, which I'll bubble right here, is luster. What does that surface look like as it interacts with light? Well, going back to this piece of quartz, you can see that it's glassy, right? Well, what about this specimen here, which we'll talk about in a moment? What does that look to you? It looks glittery. It looks very metallic-y. Well, that's a form of luster. Maybe it looks very dull. Well, when it's very dull, it can be earthy. What about this specimen here I have? We can see it's kind of shiny, but I can't see through it. So maybe it's more like a pearl. It's pearly. Well, that's what this would represent. So luster is really just how does it interact with light? So is it earthy, more like a dirt tone? Is it metallic-y? Is it more of a gray piece? Is it maybe silky, or is it waxy? So it's just really if you had to describe it to someone who couldn't see it, what would you say the surface looks like? The next one is hardness. So how hard is that mineral in relation to others? So it says here each mineral has a measurable resistance to scratching. The Mohs scale orders the minerals in a spectrum of 1 to 10. Most boxes themselves come in a box of 1 to 9. This is a Mohs hardness scale, although this is the most used, the Mohs hardness scale. But we have other ways that we can identify the hardness other than using these variation of minerals. So as we can see, I'll kind of zoom in a little bit. We can start off here with talc. Talc is in this corner here. That's the softest. And then as we move towards gypsum, calcite, we move into fluorite, apatite, feldspar, quartz, topaz, and corundum. They go from softest down to hardest, being corundum here in the box number 9. Number 10 is a diamond, and I don't make enough to have one of those, so you have to believe me that it would be there. So what we would do is we would use these specimens within this box to scratch unknown specimens. So as an example, maybe this is my unknown. So if I take my number 1 and my unknown and I scratch the unknown with my number 1, well, I can see that I left a mark, that this specimen is harder than a 1. Well, then I wipe it off and I move to number 2, and then I scratch it there. And I keep doing that until both specimens scratch each other. When they scratch each other, that means they are of equal hardness. So then I would go, this unknown specimen has a hardness of 6, and I would write that down in my notes. And then I'd move on to my next physical property, and I'd work through all of them to help me narrow down what the unknown is. I'm going to hold the box up one more time, my Mohs hardness kit. To kind of put things in perspective, talc is very fine scratchable with a fingernail. It's much, well, they use it for talcum powder. Moving down into corundum, which is number 9, that's just a poor quality garnet, which is like a gemstone. So we can see a nice little variation. We'll look more at this box in a moment. Streak is another one. Minerals, when they are scratched upon a tile, this is a white tile, they will sometimes leave behind pigmentation. So, which is really the powder form of that specimen. That being said, if you have something that's harder than the tile, then it will actually just scratch the tile itself, which means it does not have a streak color. Colors can range from red to white to blue to green. So what's interesting about streak is that sometimes the streak might actually be a different color than the specimen that you're observing. And that will be another tool that will allow us to identify what it is. And then the last one here is cleavage and fracture, is due to the structure of its chemical organization. Some minerals will either fracture or break, like glass would chip, or it would cleave in a plane, meaning that it has a nice clean cut zone. And we'll talk more about that, but that's certainly a helpful piece in identifying. So as an example, there's a mineral called calcite, and if I smash calcite with a hammer, it will shatter, but it will shatter into the exact same shape that the bigger sample was. And that's a very easy tool for us. So let's work through each one of these very quickly. Here's some examples of color. So we can see here as an example, these are all different colors here, right? You've got some orange here, green, red, some grayish brown, white, pink, brown, blue, all these colors. And what's interesting about this example I'm showing you here, these are all variations of quartz. Of quartz it is. You're welcome. I know you laughed. You probably didn't. That's okay. So these are all different variations of quartz, meaning that there's just one thing different in its final recipe that allows it to be observed as a different color. And because of that, you may have a different crystalline structure. What's interesting there is that I've used the word crystal, and I think that when most people use the word crystal, they think of like a crystal, like this milky quartz or this one in my hand. Again, this lemon quartz. Well, yes, this is a crystal, but so are all these other. Just because it doesn't look like this doesn't mean it's not a crystalline structure. So sometimes people are disappointed when they see like this piece here in my hand, which is a form of, it's orthoclase feldspar. Looking at this, it's like, well, that's not a very pretty crystal. It's like, no, it's not, but it really is still a crystal. So we've got that. So that's why I wanted to show different variations of color. Obvious, it's the most obvious, but perhaps the least helpful. So again, just because it's green doesn't mean it's quartz, because look at how many different variations of green there are. So that doesn't help us narrow down the name from either aventurine or this prasiolite. It doesn't really help us there, or jasper. Looking at luster, again, luster is, well, how does it appear to you when looking at light? This is a metallic luster because it shines like metal. Maybe it's more glassy. Maybe it's more vitreous but fibrous. Maybe it's very earthy, like this piece here. This is called bauxite. Bauxite. Bauxite is a mineral that when melted down will create aluminum. This one here, look at this perfect square. This is pyrite or fool's gold. So this is very metallic-y in its luster. So that's some examples of luster there. Again, hardness. Here's a little hardness kit. So you have talc, which is talcum powder. Gypsum, which is used for drywall, so it's a little bit harder. Our fingernail is about the hardness of a 2.5, a real one, not those talons that people glue on, like a real fingernail, is about a 2.5. Calcite, which is used as a cementing agent, is about a 3. Fluorite is 4. Apatite would be 5. Feldspar would be 6. Since I've mentioned feldspar and quartz is 7. These are your most common that we'll find. It's very rare that you'd walk around and just pick one of these other ones up on the ground. Most of what you pick up is a variation of quartz or feldspar. In fact, about 98% of the Earth's crust is a variation of quartz or feldspar because these are the two most common minerals in granite. And we know that our Earth's surface is predominantly granite. So that being said, 98% of that crust is probably made out of quartz or feldspar. Topaz, which is a nice gemstone, corundum, and then a diamond. This is a very fancy hardness kit. When I was a student and I took a basic geology course, we would have to buy one of these boxes, the Mohs hardness kit this way. So it comes with my 9 specimens there. It also comes with a little magnet. It came with my little streak plate, and then every geologist and earth scientist has one of these. You're 10 times magnifying your loop lens. And why is that important? Well, because sometimes specimens, such as this in my hand here, we can see that there's some sparkle, but maybe I want to see what those crystals are a little bit bigger. It allows me to zoom in about 10 times its size to be able to see that, oh, you know what? These crystals are not like this type where it's got a nice point to it. These might be a little flakier, and that might allow me to understand its design. Well, why is that also important? Well, because yes, this is a quartz crystal. This is a very large quartz crystal. Maybe I'm looking at something that's very, very small and I can't see it clearly. I need to look at it with my little loop lens. Streak. So here's some example of streaks. Here we have your white tile, 4 different minerals, and look, they all leave different. They're all gray in color, but as you can see, each one leaves a little bit different. So as an example, here's my streak tile, and here is a metallic-y mineral. To the observer, it's silver in color. So here's my streak plate, and I'm going to try to do this backwards, so just hang tight. So here I am, I'm going to scratch. Well, now that I've scratched, if I kind of zoom in a little bit, you'll see that it actually kind of has, if I kind of smash it out a little bit, it's very red. It's a dark iron red. Well, that's because this very shiny mineral is called hematite, and it's normally observed in a reddish color when it oxidizes. When it's in this shade, now you can see my fingers, this is, everyone's worst nightmare, glitter. This is a natural form of glitter, and it gets all over the place. Now that I've got it on my hand, it'll be on my face for maybe 2 or 3 weeks. So that's why that's helpful too, because I'd look at that metallic looking mineral and go, well, I don't know what it is, but then when I strike it upon a streak plate, I see that the residue left behind is a dark red. I can see that the mineral structure, the crystals themselves are smaller and blade, smaller pieces. That allows me to identify that, oh, this might be a hematite, and then there'd be some additional tests I can look at. I can see if my magnet sticks to it, if it does or if it doesn't. That will help me identify it too. So different attributes. These are pretty easy. This one's the hardest, which is cleavage or fracture. So meaning that, does the mineral break into a special shape, or does it just break like glass? So as an example, yes, this quartz crystal is really pretty. It's grown like this with 2 points, but if I smashed it, it would just break like glass, because this is, most of our sand is made out of this here on the West Coast. We melt down sand to make glass. Makes sense. So you probably have broken a piece of glass before, and it just shatters, right? Yes, that's what that means. Well, what about this one here? This is that piece of feldspar again. This is more blocky. When I think of the word blocky, I think of a broken brick, meaning that it's not a nice square, it's not a rectangle, but it's broken enough that I could stack them, because it has at least 2 good directions in which I can observe, meaning that it's got you can see the list here. When we talk about directions, it means a set of sides. So let's kind of talk about that. The biotite and muscovite, those are in the mica family. They have one direction of cleavage or two sides, meaning that you can easily see that there's a flat top and a flat bottom. We're using this little axe to represent how it breaks. So it breaks into sheets. So it just peels like paper. So it has a nice top, a nice bottom, which means it has two sides or one direction of cleavage. This is an example of orthoclase or plagioclase feldspars. It exhibits two directions or two axes coming in, cutting it at 90 degrees, so it's more blocky, like a broken brick. Okay, so here we have this guy here. This is a piece of calcite, which is circled right here. As we can see, it very clearly has 1, 2, 3, 4, 5, 6 sides, right? Which means that it has three really good directions of cleavage. It has, when I think of cleavage, I think of it needs to have a top and a bottom. Top, bottom, there's 1. Top, bottom, that's 2. Top, bottom, that's 3. So it has 6 sides or 3 very nice planes. If I drop this on my desk, it would break into a bunch of little pieces. It would be the exact same thing. Another fun fact about this, though, is that it has, I'll just use my field book. It has a unique optical properties. This is a field book of some notes. But if I show, you see what it does? It actually doubles the image. Weird, right? So you can see where the word rhino has been doubled, and that's part of its optical properties. Galena is a perfect cube. Galena is in the pyrite family. It's a lead ore. And then fluorite's really neat. Fluorite has four good directions or 8 sides. Fluorite looks like a double pyramid. This has not been cut. This is the way it is. But if I smashed it, it would break into that shape. It would continue to get smaller and smaller. So what I have here is a video. So when there are no perfect surfaces, it will just break like glass. So this is a piece of glass, right? This is a piece of silica. Moving down here, breakage describes how it will break. So look at this. They shatter this piece here, and look, it breaks in 2 pieces. It has a nice clean break. This one here, I didn't make this video, this little skin. From my observation, it's probably a piece of halite, which is salt, which means it's going to break into cubes. So that being said, rough course into this, I totally get it, but what we're able to do is we're able to look at specimens and we're able to go through these properties. So I'm going to go back to that list. We're going to be able to go through these properties to understand more what this mineral might be. Again, we know that there's thousands of minerals, so usually what we would have is a book, and that book would allow us to break this apart. But what we would do in the field is I would sit down and I'd go, okay, I have an unknown specimen, and I would collect all this data. Well, when I smash it with a hammer, does it break into smaller bits, or does it just shatter like glass? If I strike it on a piece of tile, does it leave behind a residue of a color? How hard is it when using my box set? How does it look with light? Right? Is it more metallic-y? Is it silky? Does it look more earthy? And then my last piece would be, okay, what color do I observe? What shade of color? So these are some of your physical properties and really the foundations of how minerals are observed. That being said, once we know this, then we're able to work towards rocks, because rocks are made out of minerals. So maybe we don't know what the rock is, but using our handy dandy 10 times magnifying loop lens, I'm able to identify what minerals are in that rock, which will then allow me to identify the rock itself. So again, I know this was a lot, but I just wanted to give you some examples of the properties that we look at when understanding minerals. And that being said, don't forget to check out the next video, the foundations of rock identification, and we'll talk soon.